Hello, my name is Sabin. I'll be talking on welding repair of dragline bucket for the mining industry. Let's get into the introduction part. The dragline excavators are extensively used in surface mining to remove overburden materials and access resources like coal. Therefore, the dragline buckets are subjected to impact from dense materials and constant operation. Therefore, it requires constant maintenance and repair, which is a costly process and huge burden for the mining industry, since the whole equipment would cost around 50 million. That's a huge cost. Therefore, a better solution needed to be provided. Therefore, laser metal deposition which is additive manufacturing process, present a better repair solution. It is a 3D printing replacement preforms without introducing the heat effects as compared to the welding. Importance of this research topic. Since the dragline buckets undergo severe wear stress, therefore it requires constant maintenance and repair. Since the traditional welding repairs doesn't offer a better solution because they cause defects and residual stress that impacts the component's life. Therefore, laser metal deposition, which is additive manufacturing that offers potential for durable repair preforms which directly are placed onto the damaged part, providing repairs with properties equivalent or even exceeding the original component. This would extend the equipment's lifespan and also improve the operational efficiency and sustainability in the mining industry. So it is a better solution compared to the welding. Some of the key observations from this study was laser processing parameters like power strongly influence the microstructure evolution and resulting mechanical properties critical for dragline performance. However, quantitative models linking numeric parameters adjustment to microstructural changes are still lacking. Therefore, by precisely tuning the laser power to systematically varying the thermal cycles, the relationship between this is important since the internal structure developed and mechanical properties can be quantified from this. Therefore, this research aimed to precisely tune laser power as a key LMD parameter influencing the mechanical properties of bonds and materials produced for dragline maintenance application. This is the machine used for the laser metal deposition. Now moving over to the research design. The material we selected is the ASI 420 stainless steel because it is commonly used in the dragline bucket teeth. So the experimental approach would be a laser deposition system will be the DMG Mori Laser Tech 65. The laser metal deposition machine equipped with a 1 kilowatt fiber laser. The samples will be built layer by layer in a rectangular plate geometry measuring 3 by 10 by 5 mm as rectangular geometries are commonly used for the mechanical testing. The ASI type would be 420 stainless steel powder which will be fed coaxially through the laser nozzle using argon as a shielding gas. A laser will be focusing on the substrate layers within 2 mm diameter spot size at a varying power levels. The layer thickness will be 0.2 mm and scan speeding of 1000 mm per second based on the equipment's capabilities. Now some of the testing that we require is the tensile testing, which will follow ASTM E8 using an Instron 5D5 universal tester with a 100 kN load cell recording maximum load, and elongation hardness will be measured using a Vickers indenter under 500 gram load as per ASTM E384. The chop impact test complying with ASTM E23, which will determine the fracture toughness, and then we'll evaluate the wear as per the ASTM G99 using a pin on disc tribometer method. After that, we'll come to the statistical analysis, which will analyze the variance between the laser power level and the effect on mechanical properties. These figures will present a relationship graphically with optimal property combination and identifying the best processing parameter for the high performance dragline application. The conclusion drawn from this research would be the determination of optimal power setting, maximize mechanical performance, and quantify models of power influence on properties critical for the dragline repairs. Let's move to advantages. So it provides data to validate computational process models, enabling more accurate and optimization and control. It also determines the optimal power settings to tailor properties for dragline repair needs. assesses feasibility and cost of laser deposition for dragline maintenance versus the welding. Some of the disadvantages are restricted sample geometries may not fully represent the structural component stresses since the samples are simple rectangular and not complex gear shapes. There is an ability to replicate the time-dependent damage mechanism as seen in service. Since the testing is on new samples, not on worn components, there is a high degree of control requires simplification compared to the real-world processing, and time and resources constraints restrict the ability to investigate all applicable alloys. Since the experiment designs a trade of depth versus breadth, the coverage of all potential materials are not feasible. So these are some advantage and disadvantage. Thank you.